right, class, let's finish this section 3.2 and finally get to the real business calculus problems. So it says use the properties of logs to simplify the function. Well, what does it mean to simplify this function? Maybe we can make a shorter one out of it. So it's what we practiced earlier and to write as a single log. So I have an ln of x to the fifth, that's fine, minus, the property says if you have a coefficient up front, where that coefficient came from is the exponent inside the log. So that 7 comes up as an exponent to x plus ln of x. And now the other thing that we said is that when you subtract numbers with the same base, or when you subtract logs with the same base, what you get to do is you get to divide the insides of it. So x to the fifth divided by x to the seventh plus ln of x. So when you add logs with the same base, what you get to do is you get to multiply their insides. And now all I have to do is simplify this a bit. So when I simplify this a bit, I'm going to get an x to the 6. So basically I have x to the 6 at the top and x to the 7th on the bottom. So this is an ln of x to the -1, or fine, 1 over x. If you want to make this prettier, that's an ln of x to the -1. Or if you want to make it even prettier, is a negative ln of x. So that's one way. Now, sure enough, maybe a different way to look at this problem to simplify it is to have done it backwards. So here, I'll write this out. The f of x from before is an ln of x to the 5th minus 7 ln of x plus another ln of x. So kind of looking at it, how I have ln of x every time, all I could have to do is bring up this 5 up front as well to make them match the others. So that's going to be a 5 ln x minus 7 ln x plus 1 ln x. And that's nothing but like terms. So combine all these like terms, 5 minus 7 plus 1 more, so that's 6 minus 7, which makes -1 many of these ln x's. And that looks pretty simple to me. Okay, so let's try this one as well. E to the ln x, what did I say happens with an e and an ln? They cancel each other out, right? So you're left with just an x. Now, what's ln of e? From the previous page, ln of e is equal to 1. You can even test it with your calculator. Again, it's e to the what power gets you an e, and that would be a 1. Yes. And then ln of 1, that's 0, because e to the power of 0 gets you 1. And ln of e to the x, again, they're going to cancel each other out. Because that's what a natural log and a log with a natural exponential function do. As long as the bases are the same, they go away. So x plus x is 2x, and then 1 plus 0 is 1. So that's what that nicely simplifies into. Okay, so let's see some example. It says, how long will it take for an investment of $80,000 to grow to $1 million if the money is invested at 6% compounded continuously? So that's your clue and your key every single time. It's compounded continuously. So what does it mean that the money is compounded continuously? It simply means that you have to use the PERT formula, right? And not the compound interest formula. So continuously, you use the PERT formula. Good. So what do we know? We want 80,000 to grow to $1 million. So the future value is $1 million. The present value is 80,000. That's what we're starting with. Okay, E is E. And we know that the money grows at 6%, so 0.06 T. So plugging all this in, as you see, the only missing variable or missing part here is the time. Yes, so how long, sure enough, is asking us for a time. So to get to this T, just as we practiced on the last page, the first thing I would want to do is divide by the 80,000. Okay, and dividing this out will get you just a 12.5. Okay, And now I need to make my way inside to the exponent, so how do I get rid of the base to just be left with the exponent? Well, I'm going to use a natural log on it. So ln of e goes away, and I'm left with ln of 12.5, whatever that might mean, or might equal to, is equal to 0.06 t. Okay, so the last thing to do is divide by this 0.06. Okay, so what is the time going to equal to? So ln of 12.5, put in your calculator, divided by 0.06. Again, put that in your calculator, is 42.1. Now, this is a word problem, and it should have units. Anytime you're talking about an investment of money, a continuous compound, the other regular compound interest formula, the time is always in years, so you better say years. And there's that. Okay. Suppose 50,000 is invested in a stock fund compounded continuously. There is your clue. So what does it mean, compounded continuously? There you're going to use the PERT formula, yes? Okay. It says find the interest rate. Okay, so after 20 years, the value is so-and-so. Find the interest rate at which the money was invested. So let's see what values are we given and what are we asked for. So it says, after 20 years, the values is this big old number. So that's what we're going to copy in place of A, 194,809.67. That's the future value. And 50,000 is what was invested presently, so the present value. Okay, e to the continuously, so that's the principal. That's the amount that it grows to. After 20 years, that means the time is 20, yes? So what's the only missing part in this formula? Well, definitely that would be the R. We don't have an interest rate. Well, guess what the question is? Find the interest rate. Okay, no problem. So it's really the same exact question from before, except for last time we were given the interest rate and we had to find the time. But it's really going to be the same exact steps to get us to this last two values multiplied together. So the first thing we'll do is divide the 50,000. So that's going to be a 3.896. Is e to the r times 20, where 20 times r, that's the same, but 20r looks better. So how do I get into the exponent? In other words, how do I get rid of this base of e so I'll be left with just the exponent? Well, anytime you need to solve for an exponent, you have to use a log. So I'm going to use a log with base e to make these guys go away. And this ln of I don't know what it is, but your calculators do, will equal to 20r. So what else do I do to get to r? Divide by 20, yes? So finally, r is going to equal to 0.068. If you put in your calculator, apparently that's what it is. Okay, so again, an interest rate is always given as a percentage. So to make this pretty, you're going to write 6.8%. So to attach the percent symbol again, what you have to do is multiply by 100, and then you can attach the percent symbol. Okay? And the last page says, an amount of $2,000 is invested at 5% compounded continuously. How long will it take for the amount to double in value? And how long will it take for the amount to triple in value? Well, let's see. Again, what's the first clue? Compounded continuously. So that means, one more time, is that what we're going to do is we're going to use the PERT formula. Yes? Okay. So, an amount of $2,000 is invested at 5% compounded continuously. How long, so find the time, it will take for the amount to double in value. So what does it mean that this amount doubles in value? It means it will become 4,000, right? Okay. So divide both sides by 2,000. Get rid of e. So put a natural log on it. If you remember that ln of 2 is 0.6931, if I remember correctly. Okay. And then divide by 0.05, so the time is going to equal to 13.86, and again, this should be years. Okay. And under the same circumstances, how long will it take for the amount to triple? Now, which amount am I talking about? It really doesn't matter. And I'll show you in a minute what I mean by that. So let's go back to the $2,000. So I have $2,000. I know how long it takes to double. How long does it take to triple in value? In other words, get to 6,000. Now, when you'll divide both sides by 2,000, so you should do first, you'll end up with a 3. Okay? And same thing, how do I get rid of the base e? Put a natural log on both sides. So ln of 3 is 0.05 t. Okay, divide by 0.05 and you'll find out that t is about 21.97 many years. Okay. All right, so the question is this: what did I mean by it really doesn't matter what you triple, or it really doesn't matter what you double? So we saw, and again, it doesn't matter which value I'm starting with, or if it's doubling or tripling time. So since I have this one in front here closer, I'm going to say, well, why did it not matter what amount am I going to start with? What if I start with $1 and now with $2,000? And I'd like this $1 to triple in value. So instead of 1, I'm going to get $3, yes? Okay. So how long will it take for the $1 to become 3? Well, again, what's the first thing you're going to do? You're going to divide by this 1, which sure enough, what does it matter dividing by 1? It looks the same. But what I really mean by this, I'll write it down in a minute, is fine, you end up with a 3, yes? What's the next thing to do to get inside that exponent? You're going to log both sides. And once you log both sides, you end up with ln of 3 is equal to 0.05 t. So does that seem to be pretty much, not pretty much, but the exact same equation that we just solved? Sure enough, yes, divide by 0.05. So it turns out that it really didn't matter if you started with $1 or $2,000 or 2 million. The tripling time, the doubling time, whatever it is, it will be the same. So it takes just as long to triple $1 as it would take to triple $2,000. It takes just as much to triple any amount p, any principal p. Once you triple it, you become, or you get 3 times p. So what would be the first step in an equation like this? Is to divide both sides by p anyhow. So as soon as you divide that p out, you're left with a 3, yes? So the amount is the same. So you might as well start with 2 million rather than $1, because you'll get to 6 million in the same time you'd get to $3 if you started with 1. So there's that. Okay. It says a company spends X $100 on an advertising campaign. The amount of money made in sales can be modeled by this function right here. And if the sales totaled 19,100, how much was spent on advertising? So let's see. So one more time. Kai, can you be quiet there? Let X be the value spent on ads, and it's in hundreds of dollars. Okay. And the amount of sales you're going to make depends on this X. That's what happens when you work with your kids around. Okay. it says the sales totaled 19,100. So you ended up with this amount of sales, yes? How much did you have to spend, or this X amount should be what, right, to get to a total sales of 19,000? Good. So how am I going to get to that X? Well, I'd say the first thing to get rid of is the 500. So we're going to minus 500 from both sides. And if you do that, you'll end up with 18,600. What else can we do to get to the X? Well, I can remove the 7,000 easily. So if I do that, I'll end up with whatever the value is. I have no idea, but since I don't have a calculator or want to take the time, I'm just going to reduce the 2 zeros at least. Okay. Okay, so now this one's definitely a different story. There's no decimal. This one's definitely a different story because what I'm going to get rid of is not a base of e, but a natural log. So how do I get rid of a natural log to get my way inside? Well, I'll use its inverse function. What's the inverse function of a natural log? An exponential function with the same base. So remember, these properties work back and forth, right? They cancel each out both ways. If you have an e to the x and you want to get to x, you use an ln. ln of e will go away. If you have an ln of x and you want to get rid to get to x, you have to get rid of ln to get to x, all you're going to have to do is put a base e under it, and e to the ln will make it go away. So here it is. E to this value is something out of your calculator, yes? And e to the ln will go away. So whatever that number is out of your calculator is going to equal to x plus 1. Now all you have to do is just minus the 1. So I had the answer in the notes there. Oh, excuse me. So apparently x is 13.29. Remember, this was in hundreds. So hundreds of dollars. Or to make it better, I'm going to multiply by 100. And make it $1,329. Boom. That makes sense. Okay. And finally, the last one. It says the population of a city is modeled by this equation where t is measured in years. If the city continues to grow at this rate, what's the rate? 0.25% per year? Continuously. How many years will it take for the population to reach 1 million? So just reading the notes, making sure this is a population and not in thousands or in millions. So that's the population. So that's how many. We start 256,114. So we want to get to 1 million. Well, we don't, but how long does it take there to get there? At this growth rate of 25% continuously per year, okay? So same thing, we've done these problems. We'll divide by 256,114. So apparently that answer is 3.9. And then I want to get rid of e this time. So to get rid of e, we'll use a natural log. Okay, and then I'll go away. So it's the same as many of the problems we just did. The last thing to do is divide by 0.25. Put that in your calculator. So the time is about 5.45 many years. All right. Ta-da, this is it.